Hello, ladies and gentlemen. On behalf of the RTI Fellow Seminar Series, it is my pleasure to welcome you all for today's Fellow Seminar. We have a highly distinguished professor from North Carolina State University. He is giving a talk today, and in fact, when I met him at a function, I asked him, Jayant Baliga, do you want to come and give a seminar at RTI? He readily accepted, yes, I will. So I am grateful to him. And I knew him for a long time. And then his name is Dr. Jayant Baliga, an internationally known expert on power semiconductor devices and a distinguished professor at North Carolina State University. Well, Dr. Baliga has so many outstanding scientific achievements. I can go on telling you for the next 15 minutes. But however, I'm going to mention few of them. In 2001, President Barack Obama presented Dr. Baliga the National Medal of Science and Technology and Innovation, the highest honor given by the US government to an engineer. And then he also received the 2012 North Carolina Award for Science, the highest honor given to a civilian by the state of North Carolina. And in fact, about a month ago, in 2014, he got the IEE, Electrical Engineers Medal of Honor, the highest award given by the Institute of Electrical and Electronic Engineers. He has written and edited 18 books, more than 540 publications, and been issued 120 US patents. It's a remarkable achievement. And he is a member of the National Academy of Engineers, which is a proud for an engineer in his country. And Dr. Baliga received his master's and PhD degrees from Renewable Polytechnic Institute, New York. And he worked before at General Electric for 14 years. And then since then, he is working at NC State last 20, 30 years for him. So it is my pleasure to ask him to give a talk today on the From Medicine to Defense, the impact of power semiconductor devices on creating a sustainable society. So, Dr. Baliga, yours. Thank you.
Well, good afternoon. And I want to thank Dr. Jayanti for this invitation to come and speak at RTI. Although you are close neighbors, I've actually never had a chance to visit RTI, so this is a privilege for me. Well, this afternoon, I'm going to speak about power semiconductor devices and their impact on society. I want to put you at ease that this is not a talk about the physics of power devices. If you want to learn about that, you should come to my class at NC State, which a lot of graduate students take. So what we'll focus on today is more how this technology serves mankind and how you benefit from it every day, perhaps not knowing about it. Certainly my neighbors were not aware of it until the president suddenly paid attention to me with a national medal. And then they said, what do you do beyond mowing your lawn and going and teaching a class at NC State? So that's when I discovered what I actually have been doing all these years. So if you look at the title, it says it's the impact of power semiconductor devices on creating a sustainable society. So I want to first start by telling you what I mean by a sustainable society. This is something we all associate with a high standard of living, where we want comfort and conveniences, comfort like air conditioning, conveniences like transportation systems. And we usually associate this with developed countries, 3 examples, US, Canada, and Australia. But these are the countries that also have the highest energy consumption. And that's because we love our appliances, we love our cars, and all of those take tremendous amounts of energy. And this leaves behind a large carbon footprint, which is the carbon dioxide emission per person. If you look at the statistics for some nations that are shown in this graph, you see that on one extreme, we have countries like the developed nations, which produce a lot of carbon dioxide emissions per capita in the range of 20 tons per year. On the other hand, we have countries who aspire to be developed countries, and countries like India, Brazil, China, and they have today a relatively low carbon footprint, closer to 2 tons per year. But all of the people who live in these countries want the high standard of living that is associated with the developed countries. The problem is that the population in these countries is far greater than those of developed nations. So today we have a carbon footprint on the average of about 4 tons or 8,000 pounds per year worldwide. But you can expect that with all this, all the aspirations of the underdeveloped nations, the carbon footprint will rise closer to 20 tons per year unless we do something about it. What I want to tell you today is about how power semiconductor technology has helped not only provide comfort and convenience, but also had an impact on reducing energy consumption and reducing carbon emissions as well. If you look at sustainable society, we can break it up into numerous sectors in the economy. Just 4 examples are shown here. These are the consumer, industrial, lighting, and transportation sectors. And in the consumer appliances or applications, you want comfort like air conditioning, conveniences like your washing machine or microwave oven. In industrial side, we want high performance with small size, for example, for robotics in factory automation systems. In the case of lighting, we are looking for good ambiance, good mood for our lighting, but also ease of installation and conveniences in terms of low energy bills. And then in transportation, of course, we all want to get everywhere quickly, so we want speed, and we want to do this in a reliable way. And everything here is always driven by cost consideration. So even if you can provide good performance, if you don't have it at a reasonable cost, it is not adopted by society. So how can we achieve this, and how can we make an impact? One very powerful way to do this is to improve the efficiency. This is so-called low-hanging fruit. Even Time magazine has published some interesting articles talking about how efficiency is the first thing we can do in terms of improving things for the world. And power semiconductors allow us to do that. Now, to understand the role of a power semiconductor device, I've made a very simplistic diagram here in the yellow box. It shows that if you have a power source and you want to control a load, the load might be a lamp. In your house, you have a mechanical switch on the wall, you throw the switch and you turn on your light. Now, we can do much better in terms of efficient controls if that switch can be regulated at very high frequencies. And that's what power electronics allows us to do. And I happen to have created, and I'll tell you more about that, a new type of power device called the IGBT that can switch at about 100,000 times per second. And this allows us to shape the way the power flows between the source and the load, enabling much higher efficiencies. Looks like my slide got a little distorted, but the high efficiency is equated with low losses inside the switch. What we're trying to do is take all the power that is in the source and deliver it to the load without wasting any of the power in between in the power switch. So the properties that we look for in these switches are low on voltage drops. You can think about it as also low resistance that reduces dissipation when current is flowing through the switch. We want fast switching capability because this reduces switching losses. And in terms of cost, we want chips, devices that work at high current densities. That way we can provide the power that we want with small chips, and smaller chips always cost less and are easier to produce. And finally, we want devices that have good ruggedness because everybody wants things to last forever. That's this way our costs are again reduced. The evolution of power devices can be charted since the 1950s. As you all know, I hope you know, that the transistor was invented at Bell Labs in 1947. And since then, it has been applied for a huge number of areas. But in the power area, a different set of companies outside Bell Labs began to develop transistors that can handle high power levels. The first of these was the bipolar transistor shown in this picture. It is a different architecture than what was worked on by the inventors at Bell Labs. This is what we call a vertical device with the collector at the bottom of the chip and the emitter at the top. This gives us two high current carrying electrodes on the opposite side, which is a better design. It also enables the device to support high voltages, which is what you want to do if you want to control high power levels. Power is the product of voltage and current. So you want more power, you need more voltage, you need more current. Now the transistor shown here is known as an NPN transistor. That's just describing the layers. You can see it has an N emitter, P base, and N-type collector. And this is the transistor that was developed in the 50s, 60s, and 70s for serving power applications, because electrons, the type of carrier that flows in this device, are much more efficient at carrying electricity than the opposite, the counterpart, which is called a hole. So it was well understood, and after 2 or 3 decades of work, well established, that NPN transistors were the right type of device to make. In addition, this transistor is known as a current control device. It has a base electrode, which is used to control the current flowing in the collector. And it is the current flowing in the collector that feeds the load that you're trying to control. So you want to have a small amount of current, small signal applied to the base to control large amounts of output power. That way, your control electronics can be made very small and inexpensive. If the control electronics is large, then it also wastes a lot of power as well. Unfortunately, when bipolar transistors were developed, after even 20 years of work, the gain that was achieved was only in the range of 10, which means that if you have a motor that you want to control for air conditioning in your house, for example, and it needs 100 amperes, you need control circuits that can handle 10 amperes. Now that is still a considerable amount of current, and it results in very cumbersome circuits that are expensive. So the bipolar transistor technology was never considered to be a great solution. So in the 1970s, a bunch of companies started developing power MOSFETs. These evolved out of the work on CMOS done by the IC industry. And the architecture of this device is remarkably similar to the bipolar transistor, except we do not want it to work as a bipolar device. So we short circuit the emitter and base of this bipolar transistor by overlapping the electrode of the source and base in the picture. And then we use a gate electrode that's separated from the semiconductor by an insulator. And that's the oxide in MOS. That stands for metal oxide semiconductor, FET. So in this device, current flows by application of a voltage to the gate. And in the steady state, when you're not switching but keeping the device in the on state, no current can flow through the insulator because of the basic properties of the insulator. So as a result, the gate control circuit for this device became very simple, something you can integrate and make it really inexpensive. So the industry felt this was a wonderful solution, something that would now replace the bipolar transistor and be used forever. Unfortunately, there was a catch, which is that when they scaled up the voltage handling capability of the device for running things like your air conditioner, the resistance inside the chip in silicon became very large. So I mentioned in this chart that you want low on-state voltage drop. That was no longer possible with this device. So the status of the industry can be described by a couplet from Rudyard Kipling. Some of you may have heard this. He said, "East is east and west is west. Never the twain shall meet." So we had a bunch of companies actually on the East Coast, like GE, who made bipolar devices. They had their own manufacturing practices, and they had their own end customers. And now you had another group of companies, like International Rectifier and Siliconics, on the West Coast, it so happens. and they had their own processes, manufacturing practices, and end customers. And it was felt that these technologies were basically incompatible. Well, I took a brave step in the 1980s and proposed merging these two technologies into a new kind of device, and that was called the IGBT. So this structure uses a gate, MOS gate, to control the flow of the base drive current to a bipolar transistor. So it has both the MOS technology and processes to control the input current, and then it has a bipolar transistor to carry the output current. Now, today the IGBT is very, very well established. There are dozens of manufacturers. It's used for a huge variety of applications, which I'm going to tell you about. But when I proposed it, it was not met with great enthusiasm. Firstly, my skeptics pointed out that this device had a very bad bipolar transistor design. It used holes instead of electrons, and the prevailing wisdom was you want to make NPN transistors. And I was proposing using a PNP transistor. So they considered that to be a rather major disadvantage. But even worse, I had proposed a wide base PNP transistor, and it was again prevailing wisdom that you need a narrow base transistor to get good current flow through it. And finally, they felt that the gate structure in this device just would not deliver the current required to pump that PNP transistor and make it work. And finally, to put the nail on the coffin, they said that now I have created a 4-layer device. It has an N source, P base, N drift, and P plus collector. And such devices were known in the 1950s and 60s to produce thyristors, which latched up. And this device was considered to be one that would destroy itself before it could carry substantial currents. So all around, it was considered a rather badly thought out proposal. But I insisted that it was a good idea and convinced GE management that I knew what I was doing. I even had a meeting with the chairman of GE because he heard about how its impact could be right across the company. And by the fact that GE had this very broad portfolio of products, I was able to get support. And I took this device from concept to production in less than 1 year, which is somewhat remarkable if you have any experience trying to do this. Most often at GE, we would build new ideas in our research labs. We had a big research lab like RTI in Schenectady. And after developing a unique process for an innovation, because it usually cannot be made in a manufacturing line, we would then have the onus of transferring it to production, and that would take several years plus a huge investment on the production line because you have to bring in new equipment, new processes, stabilize them, get the yield, and so on. I short-circuited all that and got the IGBT out in less than a year. And again, the great thing about GE is the diversity of the portfolio of products. GE, I think you know, makes appliances. They used to make even small appliances that they sold to Black & Decker. Those are the things on your table in the kitchen. And then they had, of course, a big lighting division. They wanted to build a numerical controls division for factory automation. They had a very big medical division and so on. So once it caught on and started getting used everywhere, of course, there was no going back, and it became a very successful technology. So the symbol for this device is shown on the upper corner. I'm bringing that up because when I show some circuit diagrams in the upcoming slides, I want you to be able to recognize what the symbol looks like. All right, so today we are served by two basic technologies, the MOSFET and the IGBT. The MOSFETs are used in lower voltage applications, which also happen to be lower power applications, prominently in power supplies for your computers and laptops. They're used in automobiles for your power windows, your power doors, your air conditioning systems. In your communication devices, they're used for power management. And in aerospace, they would be used, for example, on the space station for providing the power and so on. Then the IGBT serves all the higher power, higher voltage applications. like the consumer sector, the transportation sector, the medical sector, renewable energy, and the industrial sector as just a few examples. I'll tell you more about them in my lecture. So let's start by looking at the medical sector. And here are some examples of places where the IGBT is used today. The X-ray machine was among the first, where the power supply for the X-ray is now regulated by using IGBTs. You, of course, have a similar X-ray tube in the CT scanners, and unless you have an extremely well-regulated power supply for the X-ray tube, you will get really lousy images. So the IGBT is a critical component in improving image quality. In MRI scanners, it is used particularly for driving the gradient coil. If any of you had an MRI scan, I think you know those pulses that you hear in the machine. Those are the gradient coils being powered, and this allows you to get sectional images during the MRI scan. They're used to run the transducers in your ultrasound machines. Here's an example of a scan that most women take during pregnancy. And then they're used for driving lasers in numerous applications, LASIK surgery being one case. But my favorite example is the portable defibrillator, which happened in the late 1990s. And I recall sitting in my office at NC State and getting a call from one of these companies that said, we're about to release the first portable defibrillator, and we could not have done this without your IGBT, and we thought we should let you know. That was very unusual, but most of the time they just use it and don't tell me about it. So what is the IGBT doing? It is responsible for controlling the shock pulse applied to resuscitate the victim, and this turns out to be a pretty powerful burst of energy. It has a 100 kilowatt energy level, power level, and it has to be applied at a 2000 volt level. And only a chip like the IGBT can provide this function in a compact form that can be put inside a small portable defibrillator. You know, they're the size of a laptop today. And the American Medical Association says that this is saving on the order of 100,000 lives every year in the United States alone. So this is a totally unintended application for my device, because I was working at GE and working towards applying it for motors, lamps, and so on. So that's a wonderful outcome that I never expected. Turning to the consumer sector, I want to share with you places where my device is now used in your everyday lives. So the next time you run these appliances, perhaps you will remember this lecture. One of them is the washing machine, and this happens to be a picture I took from a Toshiba drive. So the IGBTs are used to control the motor, and this got rid of all the gears that used to be used before for controlling the different directions of motion, and all that was very mechanical and unreliable. So now it's gone all electronic, and it's become much more sophisticated in terms of all the functions you can do. Another place that it's used is in your induction cooktops. These are now very popular in kitchens. And in an induction cooktop, you have a coil like the one shown on the upper right-hand side, and you place your pot on top of that coil, and it couples energy through an inductive process. You can also have tabletop models of these induction heaters. So this is all done today by using IGBTs working at a frequency in the range of 30 kilohertz. Another application is in microwave ovens. You might know that the energy used to cook the food is derived from a magnetron, but the magnetron requires a very good power supply to run it. And using the IGBT, they were able to build this power supply so it could run at much higher frequencies in the range of 20 to 30 kilohertz. That allowed us to shrink the size of the transformer. And I was surprised to learn that this actually brought the weight down from 4 kilograms to only 400 grams. And I think this is wonderful, particularly for those who are installing the microwave oven. But even if you have a portable unit on your kitchen, and you want to move it around, it's wonderful that it's not as heavy as it used to be. Some of you may have plasma TVs, and IGBTs are the devices used to drive the pixels. They not only used to create the picture, the image, but they're also used in the power recovery circuit now. This has enabled reducing power consumption by at least 20%. Turning to the transportation sector, it started out by using IGBTs in smaller vehicles, like the first electric car. I recall at GE, when I was still there, GM was trying to develop something called EV1, the first electric car. Unfortunately, they didn't pursue that to commercialization, but they used IGBTs for that. Today, the power level that an IGBT can control has grown over 10 megawatts, and consequently, we can use it even in high-speed trains, like the Shinkansen bullet train, or the TGV that runs in Europe. Some of you may have gone on it. So these are trains that run at 200 to 300 kilometers per hour. Here's a quote from Alstom that has installed IGBT-based drives, and they state that their Onyx traction system, I can't read it from here, so, using IGBTs has produced 50% reduction in volume, 30% reduction in weight, 33% reduction in life cycle costs, and 50% improvement in reliability. That's a pretty big payoff for any technology. So these are finding use in a lot of places. In China, they're installing 18,000 kilometers of high-speed rail by 2016. Some of you may have come across this. In India, they're running diesel-electric trains. In the United States, we're not so gung-ho on high-speed rail. We should get there someday. But you do find the IGBT used in places like JFK Airport for your local transportation, or maybe in Atlanta, and certainly commuter rail. So you will be riding trains which use these devices. Of course, electric vehicles are all using IGBTs. The Toyota Prius uses a IGBT module. And what does the IGBT do inside this? Well, firstly, in a hybrid car, you have both a ICE engine, the internal combustion engine, and you have battery power to run electric motors. That's why it's a hybrid. So the IGBTs are used in the ignition systems of all internal combustion engines, and I'll talk more about the impact of that later on. And primarily, they're used to control power flow from the battery. And they're used in all the modes, like the electric mode, the hybrid electric mode, the battery charging mode, and even regenerative braking. So if you're running a Prius, next time think of me. If you have an electric car, like the Tesla Roadster, I'm sure lots of you have Roadsters, or the GM Volt, the IGBT is used to control energy from the battery to the motor, but it's also used for the charging circuits that you would have to install in your home, or some of them are now being installed on streets. And in fact, on our Centennial campus, we have charging stations at various locations. I want to just quickly show you that that's not the only, those are not the only places. You find them in electric buses, like this Hertz bus. You find them in electric trams. This fall, I was in Europe receiving my IEEE Medal of Honor, and we went to Austria and rode on some of these trams. And I'm told that the IGBT allowed bringing the platform of the tram lower down so that people could walk in and out more conveniently. And it was certainly really convenient to use those trams. It is used in the new all-electric airplanes for controlling all the actuators now. They're moving away from hydraulic systems to electrical actuation. The 787 Boeing aircraft uses it, so does the Airbus. It has now reached power levels where they're starting to run big ships, like this LNG, liquid natural gas carrier. And I was astonished to learn it is even in cruise ships. It has nothing to do with bugs and all that. It just runs the propeller and the whole electrical system of the ship. In terms of the industrial sector, I was fortunate to be at GE when they got interested in getting into this market in terms of numerical controls for factory automation. So I created a complementary pair of devices. The device I showed you in the earlier picture was an NIGBT. I also invented and developed the PIGBT, and this led to a product called the GE Genius I/O product. And I looked it up, and it's still in existence, which is interesting. They still have a Genius I/O product. So that allowed GE to win the first Saturn motor car production plant, which was very, very exciting for GE, and moved them up from nobody in the business to #2 in the world. So this is very exciting. Today, IGBTs are used to run all the motors in robots. There's a picture of an assembly line with robots. And it has lots of other applications, which I don't have time to get into, but you can look at steel mills or textile and paper mills. Everywhere there are motors, you use these devices. They're used in induction dryers, sometimes for agricultural products. Arc welders happen to be very popular for use of IGBTs. In fact, it's fashionable to say that it is made using IGBTs. When I go on the web, I see so many companies in India and China, they say IGBT controlled arc welder. I said, wow, it's become a fashionable item. And it's used in milling machines and high-speed drilling machines. So it's all over the place in terms of the industry. Now I want to speak about the lighting sector, and I'll spend more time on this later in terms of social impact. But one of the places where it has had a huge impact is in creating the compact fluorescent bulb. So this is a circuit diagram for running a CFL tube, and the IGBTs, as you can see in this diagram, control the different functions. And it is not a device that just runs in steady state. You have to first do a preheating function to get the lamp to ignite. Then you have to apply a high voltage to get a gas discharge. And then you have to move the operating point to work in steady state at high efficiency. So all that is done by using IGBTs in that circuit. Other places for lighting, which I could relate in terms of you folks, would be in digital cameras, to flash in your cameras, and perhaps in your cell phones. Here, the IGBT is the device that controls the ignition of the xenon bulb. Now, you may or may not know this, but a xenon bulb requires a heck of a high voltage, 320 volts, and you have to derive that from your 3-volt battery that's inside your camera or your cell phone. In addition, it requires 150 amperes of current to get the discharge and the amount of light that you want for your pictures. All that is done with a tiny little IGBT that has to fit inside these smaller and smaller cameras and cell phones today. So it's pretty amazing to see what people have done with this technology. And then I thought you might find it interesting that next time you go to the movie, the arc lamp, the xenon arc lamp in the movie theater is being run with IGBTs, even the IMAX theater. Let me move on to the defense sector, because the title of my talk is Medicine to Defense, so I better say a few words about defense. The Navy got very interested in moving away from hydraulic systems to electrical actuation many years ago in the 1980s. And they were strong proponents of a concept called PEB, Power Electronic Building Blocks. And they wanted all kinds of functionality to be put inside this. Unfortunately, the Navy backed the wrong horse for semiconductor devices. They chose a technology known as the MCT and spent tens of millions of dollars, and the device never came to being. Meanwhile, the IGBT technology was neglected in the US and was picked up overseas. So it was first produced in huge volumes in Japan and Europe, and then all the US companies came back later. So today, all these PEBs are built using IGBTs. That's the irony of the situation. Here's an example of a warship drive that they are implementing using these PEBs. The advantage of this system is a lot of redundancy in terms of, for example, power sources. They can use fuel cells, batteries, flywheels, and other sources, and then convert this into a single DC power bus from which everything can be driven, like the propellers, including the weapon systems. In terms of scaling things up, they're now applying this technology even in aircraft carriers. For example, all the weapons elevators, the hangar doors, all the lifts, they're all run using this technology. And they are now developing aircraft launching systems, which is a really interesting application. It's called a rail launcher that launches airplanes into the air. And I'm told they've successfully launched one aircraft in a demo, not on actual ships. In a nuclear submarine, this has come in very handy because they want what is called a quiet drive. Obviously, if you're in a nuclear submarine, stealth is what you're really looking for. And any kind of signature that your enemy can detect is bad news. So they have developed these very special quiet drives using IGBTs. The Army is not being left behind. They are replacing the traditional Bradley fighting machine with electric vehicles. This is the topology they've chosen, a bidirectional converter using IGBTs, and are implementing them now. The Air Force is also not far behind. They're developing the fighter jets. F-16 has been advancing from mechanical and pneumatic drives to a more electric aircraft drive where electrical systems are used for all the actuation. I would be remiss if I didn't talk about the renewable energy sector because this technology plays an essential role in making that happen. So as you know, wind power is being installed in a major way in most parts of the world. The US Department of Energy says that wind alone could supply the entire United States, offshore wind, capacity of 900 gigawatts. And solar energy is estimated to provide 10,000 times the needs of the globe. So in the case of solar cells, the photovoltaic cells produce very small DC voltages. And what we need to do to use them in terms of our homes is to convert it into a very stable 120 volts AC 60 hertz, which is what you get in your house or in the sockets in the room. So that is all done by using IGBT-based inverters. And these are, of course, installed in solar farms, in rooftops, become very popular. Wind power has somewhat of the same issue because the input energy is highly variable. Wind blows harder, blows less hard, changes all the time. So you have to convert that into a stable 60 hertz, 120 volts output in order to feed it into the power grid. So that is all done using IGBTs, and the module is shown. What is interesting to read is that this technology helped get rid of the gear train, which used to be located on top of the windmill. You know, they're on top of huge towers, and that, of course, was a great improvement in terms of reliability as well as weight and size. Electronic Design Magazine in 2004 stated that progress within the IGBT technology has made the biggest single contribution to wind turbine advances over the past several decades. So having given you sort of a smattering of all the applications, and these are not all, I even came across a paper that the last Higgs boson, which was discovered using the Hadron Collider. Are you all familiar with that? They got a Nobel Prize for it. The IGBT was in the power supply. So I said, wow, this is really cool. Okay, so what I want to talk about now is the social impact. And I borrowed this picture from Kintish, who published it in The Bridge in 2012. So it's a nice diagram to tell us how society thinks. So society generally wants improved living conditions. And to do that, we demand more goods and services, which of course make greater energy consumption. And if you deliver this energy using fossil fuels, you get more carbon dioxide emissions. That leads to more carbon dioxide in the atmosphere and global warming, which is considered a degradation in our ecosystem. So that is, of course, opposite of our improved living conditions, right? So we're in a vicious circle here, and we need to do something about it. How can we break this? Well, we can conserve on goods and services. I don't think that's politically very popular, so we'll instead have to do something like more efficient delivery of these goods and services, or deliver the energy using renewable sources, Failing that, we have to do carbon sequestration or geoengineering. I've heard of proposals like putting particles in the atmosphere that will reflect back the sunlight. I don't know how effective that will be. Or eventually we have to do adaptation, like building seawalls to keep the ocean from our doorstep. So what can power electronics, power devices do? We can really make a big impact on the efficiency side. So I'm going to give you 3 examples where this has had a dramatic impact. The first is in efficient air conditioning and refrigeration, which is basically motor control. The second is efficient lighting with CFLs, and the third is efficient transportation. Now, when it comes to transportation, we have relied on the internal combustion engine for over 100 years. And this is, of course, based on using gasoline as the fuel. Today, cars and trucks consume about 76% of the fuel. And internal combustion engines work by using this gasoline in the cylinders of the car, and you need, of course, a spark plug to ignite this gasoline mixture. That was done for a very long time using the Kettering mechanical distributor. I don't know if any of you recall doing tuning of your cars in the 1970s. I tried it myself. You had to use a little strobe light and get under the hood and tune the car, right? Otherwise, your fuel efficiency would get pretty bad. Today, it's all gone electronic. You don't have to do that anymore. And that's because it became possible to make electronic ignition systems using IGBTs. Now, the advantage of using electronic ignition systems is you can very much more precisely control the spark plug. And that has enabled the industry to use a leaner fuel mixture, which of course helps us in terms of efficiency, and I'll talk about that. Over the years, billions of IGBTs have been sold by multiple semiconductor companies just for this one application because of the size of the market. So what is the impact? Well, the way to look at this impact is to look at the gasoline consumption, and this chart shows the gasoline consumption in the United States over the years and also around the world. In the US, we've been using between 100 and 200 billion gallons of gasoline per year. In the world, it's somewhere between 500 and 600 billion billion gallons of gasoline. So what we have found is that the electronic ignition system has improved the fuel efficiency by at least 10%. There have been numerous studies done which show this. So if you take this gasoline consumption and compute how many gallons we have saved over the period shown here from 1990 to 2010, it amounts to a staggering 1 trillion gallons of gasoline. So that's not bad for improved efficiency or reduced energy consumption. Now, if you want to calculate the impact of this on people, you have to know what they're paying out of their pocket, right? So here's the price of unleaded gasoline in the United States. And it stayed at a moderate level of about $1.50 for a long time. But then in the 2000 timeframe, it started going up. And today we pay around $3 last time I went to the gas pump. In Asia and in Europe, if you travel, you will find that the price of gasoline is considerably higher, approximately 3.5 times more. So using the price around the world on the average and the gasoline consumption savings that I gave you from the previous chart, you can compute how much cost savings people have derived. And it amounts to over $5 trillion. If you don't burn this gasoline, then of course you reduce carbon dioxide emissions, because each gallon of gasoline produces 19.4 pounds of carbon dioxide. So by reducing carbon emissions, by reducing gasoline consumption by 1 trillion gallons, you end up with a huge reduction in carbon emissions as well. And in the world, it amounts to somewhere between 1 to 1.2 trillion pounds per year. So this adds up to a CO2 savings of over 22 trillion pounds. I want to now talk about air conditioning and refrigeration. Some of you may be aware that motors consume most of the electricity that we use. Approximately 2/3 of the electricity in the world is used to run motors because they're so prevalent in your homes, in factories, etc. The DOE report shown here indicates that In the residential sector, the major consumption is in refrigeration and in air conditioning. The same also holds true for the commercial sector, except now we're talking about things like vending machines and bigger air conditioning systems like for this building. So the old technology used to perform this function was to use an induction motor run directly off the line. And as you know, we get electricity at a frequency of 60 hertz. So the induction motor is very efficient, and it runs at some multiple of this 60 hertz, depending upon the windings of the motor. And it has excellent efficiency of 95%. The problem is that if you want to regulate the output, then you have to use something called a damper. And a damper basically throws away a huge amount of energy before it reaches the load, because the output of the motor is constant. So you end up with an efficiency of below 50%. So in the 1980s, we set about at GE to create what are called adjustable speed drives. Here we take the fixed input 60 hertz power from the utilities, we convert it into a variable frequency output power. And that frequency can range from below 60 hertz, could be 10 hertz, go all the way up to 10 kilohertz, 10,000 hertz. And so now you can feed that variable frequency power to your induction motor, and it will now spin at the appropriate speed, a multiple of that frequency. And you don't need the dampers anymore, making the efficiency go up by at least 40%. And the first IGBTs that I actually designed were for this purpose at GE, and we commercialized those in 1983. And GE actually delivered these to Trane and Carrier, that are the big builders of air conditioning systems in your homes. Here's an example of some energy studies. This was done by Eaton, and it shows that if you're running at full 100%, the damper is basically not doing anything, so you get good efficiency, and so does the adjustable speed drive. It is when you throttle back that the damper wastes a huge amount of energy, and with adjustable speed drives, ASDs, we can get 40% energy savings. Actually, the energy savings can be far greater. You can find examples in the literature. For example, Mayflower Vehicle Systems that builds Aston Martin cars projected 88% reduction in energy use using adjustable speed drives. So to quantify the impact of this on society, you have to, of course, know how much electricity is being consumed, and it amounts to approximately 20,000 terawatt hours per year. And if you convert that into power savings, because we are using 40% less electricity using adjustable speed drives, then you get the numbers shown on this chart. Now, I've shown this chart with three graphs, 25%, 50%, and 100%, to show you that the market penetration is not 100%. In other words, adjustable speed drives are more expensive than the old technology, so there are still places in the world where the old technology is still used. But between the developed countries and the developing countries, we have a market penetration today of about 50%. So if you look at this chart, then we are saving power in the range of 200 to 300 gigawatts. And if we don't have to produce this electricity, then we get a huge savings for the utilities, because each coal-fired plant produces about 1 gigawatt of energy, and that costs between $2 and $3 billion. So if you don't have to build 300 gigawatts of capacity, then you save a lot of money in terms of the utility investments. If you want to calculate cost savings, then you have to understand the price of electricity. In the United States, it's about 10 cents per kilowatt hour, which is about the cheapest in the world. But if you go to Europe or other parts of the world, then it's much more expensive. So on the average, the worldwide electricity cost is about 20 cents per kilowatt hour. So factoring that into the cost savings, we find that we're saving between $300 and $500 billion per year. And that adds up to a total of over $8 trillion over the last 20 years. Considerable amount of savings for consumers. Of course, if you don't have to generate this electricity, then you can also reduce carbon emissions. You know that most of the electricity is generated today using fossil fuels, coal and natural gas. In the world, it amounts to about 68%. And the average carbon dioxide emission from fossil fuels is 1.1 pounds per kilowatt hour. So if you factor in that 2/3 of this electricity is going to motors with 40% power savings using ASDs and a 50% penetration rate, then you get carbon emissions shown here, which is between 2 and 3 trillion pounds every year. So that adds up to over 46 trillion pounds over the last 20-year period from 90 to 2010. Lastly, I want to talk about social impact from the point of view of lighting. For a long time, we relied upon incandescent lamps. This is a relic of the Edison era. He's, of course, very famous for developing the filament for these incandescent lamps. It basically works by heating the filament to 3,000 degrees centigrade. Less than 5% of this energy is used to produce the light. That's why the bulb is so hot if you try to touch it after it's running. It is very inexpensive and considered disposable, but I'm always annoyed that it only ran for about 1,000 hours. I don't know how you feel about it. But lighting, as a consequence, consumed about 1/5 of the electricity in the US and in the world. We did much better by introduction of compact fluorescent lamps. Some early work that I was involved in at GE were codenamed Triac and Haylock. These were code names used by GE, and eventually the product itself became CFLs. The challenge here was to fit the electronics within the small base of a CFL lamp. And why do you keep the base small? Because we want the same screw-in socket to go into your existing lamps. They didn't want to rebuild everybody's infrastructure, right? It's much harder to sell something if you tell the customer, go buy a new lamp before you can use my, or what should I say, lamp meaning the lighting fixture before you can use my bulb. So the electronics had to be miniaturized, and IGBTs enabled us to do that. And this is what enabled commercializing CFLs. I think you probably heard that for a 60-watt bulb, it only takes now 15 watts of electricity to run the bulb. So that's a 75% savings in energy, and it has a relatively long lifespan of 10,000 hours. This technology has been very widely adopted around the world. In Japan, by 1996, 80% of households had CFLs. In India and China, there are major programs to replace incandescent lamps with CFLs. And today, there are over 14 billion CFLs in use. In the US, we're a little bit behind the curve here. There are about 1.2 billion CFLs. So to quantify the impact, let's assume that a CFL is used for 6 hours per day. And if you take a 45-watt power savings per bulb, then you calculate as much as 600 gigawatts of power savings. And of course, it has grown slowly over time because CFLs were adopted over a long time frame. So of course, if you today don't have to consume 600 gigawatts, then utilities save on the tune of $1.9 trillion. If you want to quantify the benefit to the customer, we can use the same 20 cents per kilowatt hour of energy savings, and customers are saving to the tune of nearly $300 billion a year now. And if you added this up over the 20 years, it amounts to about $1.8 trillion. Of course, if you don't consume all that electricity, then you get the carbon dioxide reductions using the same calculations that I went through before for the adjustable speed drives. And you can see that trillions of pounds of carbon dioxide are reduced, which add up to about $10 trillion over the last 20 years. So here's a summary which tabulates all these benefits in terms of gasoline reduction, in terms of energy reduction, in terms of cost savings. And as a summary, the worldwide utilities have saved about $3 trillion as a consequence of not building 930 coal-fired plants. And consumers have saved to the tune of $15 trillion because of not consuming gasoline as well as electricity. In terms of carbon dioxide emissions, these are the numbers that I shared with you earlier, put into a table. And as a summary, you can see that we have reduced carbon emissions by 78 trillion pounds. Now, to give you a feeling for how large this is, I want to remind you that global carbon dioxide emissions per capita were 8,000 pounds per year, right? And if you assume 7 billion people in the world, then we are consuming, or putting out, I should say, 56 trillion pounds. So over the last 20 years, we have reduced carbon dioxide emissions with this technology to the tune of 1 year of production in the world, which is quite remarkable. So I want to conclude by saying that power semiconductor technology has had a huge impact on society. Most people are totally unaware because this is what we call an embedded technology that's hidden from the eyes of society. As I said before, my neighbors were totally unaware of the fact that what I had invented was in their homes, in their cars, in everyday life. Only when someone like the president, puts a spotlight on you and on this technology, then people take notice. So this has had a huge impact on comfort, convenience, and health. And I think I can safely say that it has enabled a sustainable society with improved quality of life for billions of people around the world. So thank you for your attention.
Thank you for the nice talk. It was clearly a nice overview of the application of power electronics and semiconductor devices. Now, from your perspective of where the field is going, what is the next big thing for which there is a need? Because as you were going through my first questions, I was like, well, there is a limit to the power. Should a new technology be developed for higher power? But that goes against all this efficiency talk. So what is the next big thing? Something that achieves the same with less power, or something that goes with higher power?
I'll show you some slides in answer because I was anticipating it. But let me firstly say that power technology, as you saw, has penetrated all aspects of our lives, all sectors. I was trying to even ask myself, is it applicable to the financial sector? And the answer is yes, because they rely so much on UPS, uninterruptible power supplies, because all their financial transactions are occurring continuously, and I found that they lose $6 million per hour of interruption of power. And all that is done with this technology to prevent loss of power. So it's pervasive, and so the question now becomes, how can we expand its applications? How can we make things even more efficient? And one place we're doing this is on the utility side, where we are developing a new way of making power distribution. The old model is a huge power source, like a nuclear power plant or a coal-fired plant, and then you transmit the power long distance and distribute it. The new model is a micro environment, which we sometimes call a microgrid. So at NC State, we have something known as Freedom System Center, sponsored by NSF, which focuses on technologies needed to create this environment. So it has energy sources like wind and solar. It has energy storage, because these sources are not running 100% all the time, right? I mean, you need power in the night, and solar doesn't work. Wind comes and goes. And so it's an entire ecosystem that we are examining and trying to enable. And that's just one example. In terms of technology, this is where I had a few slides, so maybe I'll share them with you. The future is believed to be wide bandgap semiconductor materials. And I have to go back all the way to 1980, when I derived the first fundamental relationship between the resistance inside a power device, which controls the on voltage and losses, and the material properties. Surprisingly, nobody had taken the effort to do that. So I derived this equation, which is in the blue box, and I proposed replacing silicon with other materials. In fact, at GE, I first did this with gallium arsenide, if you're familiar with materials, and we made some products. Then I wanted to do this with other materials, which is why I moved to NC State. So when I came up with this, I thought everybody will think I'm like Socrates, a great philosopher. Instead, they thought I was like Chicken Little, screaming that the sky is falling down. They said, silicon is great, we don't need these wide bandgap materials. So it's taken a long time, and only now, in 2000 and beyond, we're starting to see commercial product come out in this area. And in particular, it has happened with these new materials, silicon carbide and gallium nitride. So a lot of this work was done through NC State, my own work, as well as the work in material science, which created Cree, as you know. I think they are your neighbors here. And then after we showed high performance of these devices in my center in silicon carbide, it started getting worldwide interest, and now there are at least half a dozen producers. The major one is Cree and also Infineon. You may also have heard about this new manufacturing institute that was recently announced this year by President Obama at NC State. This was a competitive proposal which we happened to lead and win. It's a $140 million program now to make this manufacturable. And it brings together the whole ecosystem to make these kinds of devices viable in terms of reducing cost. So it ranges from R&D done at universities to wafer suppliers, basic materials, to companies that make devices, to production facilities that would reduce the cost. So this is believed to be the next big wave. And if you think that the US is putting a lot of money, $140 million, you will be surprised to learn in Japan they've already put in $500 million, and in Europe something equivalent. So unless we are really rigorous about following through, the actual manufacturing and jobs will actually go overseas. So this is our opportunity to try to bring this technology base to the United States. So I hope I answered your question.
What is the device cost?
The cost of the device, the question, what is the cost of the device? The cost of the device depends on the power it's handling, so it depends on its voltage and current rating, and so it's huge range from under $1 to $100, you know, but it's not enormous either. Yes.
So GE is the one selling these devices?
Actually, GE abandoned the semiconductor market. Jack Welch decided to sell the business. This is another reason I left GE. Yes, they said they would source this technology from other companies because they made most of the money. In fact, most of the money is made by GE in the systems like air conditioners or drives for trains. The semiconductor components don't make that much money. So when I first invented it, his reaction was, this is great, we embargo this from everybody and we cash in on all the uses, like making appliances, drives, and so on. And that was very hard for me as a technologist not to be able to talk about my great innovation for many years. But fortunately, no one else came up with it before we announced it, and that way I still got some recognition.
Good afternoon, sir. You mentioned that the U.S. Navy some years ago went with the wrong choice, MCT technology rather than the IGBT, and that overseas that was being used much more. Currently, what is the primary source? Is it here in the U.S. or overseas?
Okay, so the question was about the evolution of the IGBT and how the Navy chose a different technology. Let me just say that it was not just the Navy. A consortium was formed in the United States between EPRI, which represents the utilities, the Department of Defense, which Navy was part of, and Department of Energy. And they actually decided as a collective group to only support the MCT. And they wrote a paper on this, which is published in the proceedings of the IEEE. So I'm not making this up. You can read it. Okay. In fact, when I came to NC State, they first said they wouldn't fund me because I was an IGBT guy. It was pretty bad. So what happened is that once GE announced this as a product and people saw its utility, the Japanese companies were the first ones to pick it up. So about half a dozen of those companies started making products. And then the European companies started doing it because they're very big on traction and, you know, all the locomotive drives and so on. And then subsequently, the US companies started doing it as well. So we do have producers here, IR, Motorola, several others. But it came kind of full circle, first went outside. Correct. Meanwhile, the MCT was never successful because it had some production issues, some basic challenges in how it works. So.
Okay, I thank you very much.